Hello everyone, welcome to my YouTube channel. Myself, I am Ishwardhan, currently pursuing my education in Sri Venkateswara College of Engineering. In this video, we are going to discuss about basis and dimension of vector space. So, in linear algebra, a basis for a vector space is a set of linearly independent vectors that spans the entire space. The dimensions of a vector space is the number of vectors in its basis. Essentially, the basis provides a minimal set of vectors needed to represent all the other vectors in the space through linear combinations. If the basis vector is denoted as v1, v2 up to vn, then any vector in the space can be written as a linear combination of these basis vectors a1 v1 plus a2 v2 up to an vn. Introduction to basis and dimensions of vector space. A vector space is a collection of vectors that satisfy certain properties such as closure under addition and scalar multiplication. Basis and dimensions are the fundamental concepts in linear algebra that helps us to understand the structure and properties of vector spaces. In this presentation, we will explore the definitions and properties of basis and dimensions in a vector space. So, the dimensions of a vector space. Consider H is a set of linear combinations of the vectors as we see in the image. So, clearly in this, V1 is not equal to 0 and V2 is not a multiple of V1, but V3 is a multiple of V2. By the spanning set theorem, we can discard V3 and still have a set that spans H. Next. The definition and properties of basis of a vector space. A basis of a vector space V is the set of vectors that are linearly independent and span V. Linear independence means that no vector in the basis can be written as a linear combination of the others. Linear independence refers to a set of vectors in a vector space where no vectors in the set can be expressed as a linear combination of others. In other words, the vectors are not redundant, they provide a unique information. Spanning means that every vector in V can be expressed as a linear combination of a basis vector. Like spanning refers to the a set of vectors that are combined linearly to generate any vector in the vector space. It is a set of vector spans a space. Then a vector in that space can be represented as linear combination of the vectors in the set. Next is illustration with a two-dimensional vector space. So let us consider a vector space V in R square. The vectors 1, 0 and 0, 1 from the basis for V because they are linearly independent and span V. Any vector V can be expressed as a linear combination of 1, 0 and 0, 1. Next, definition and properties of dimensions of a vector space. A vector space can have any finite or infinite number of dimensions, like the dimensions of a vector space in the number of linearly independent vectors in its basis. For example, in 2D space, the basis vectors are 1, 0, and 0, 1, making a two-dimensional vector space. But in 3D spaces, the basis vectors are 1, 0, 0, 0, 1, 0, and 0, 0, 1, making a three-dimensional vector space. The dimensions of a vector space V is the number of vectors in any base of V. It represents the size and or the number of degrees of freedom of the vector space. So the dimensions of V is denoted as dim V. Next, the properties of dimension. Key properties of vector space dimensions. Any two bases of vector space V have the same number of vectors, hence the same dimension. The dimensions of the zero vector space is 0. The dimensions of a vector space V is always a non-negative integer. So consider H is the set of linear combinations of vectors v1, v2, v3 and v4. In this, clearly v1 is not equal to 0, but v2 is not a multiple of v1 and but v3 is a multiple of v2. By the spanning set theorem, we may discard v3 is still have a set that spans H. Next is relation to basis and dimension of linear independent sets. A set of vectors is linearly independent if no vector in the set can be written as a linear combination of others. A basis is a linear independent set that spans the vector space. The size of basis corresponds to the dimension of the vector space. Next is the relationship between basis and span. A basis of a vector space spans the entire vector space. Conversely, any set of vectors that spans a vector space can be reduced to a basis by removing linearly dependent vectors. The basis of vector space and its span are closely related concepts. A basis is a set of linearly independent vectors that can generate the entire vector space when combined through linear combinations. In other words, the basis vector from the minimum set required to represent all the vectors within that space. And the span is a set of vectors, is the set of all possible linear combinations of those vectors. The span includes all the vectors that can be created by scaling and adding the vectors in a set. A basis is a specific subset of these vectors and the spans of space, but also doesn't contain any redundant vectors. Next is the practical applications of basis and dimension. Basis and dimensions are the fundamental concepts in linear algebra, which is widely used for various fields such as physics, engineering, and computer science. They also helps us to solve the linear equations, analyze transformations, and understand the structures of vector spaces. Its applications include image compressions and computer graphics. In computer graphics, basis vectors are used to define coordinate systems and transformations representing objects as linear combinations and of basis vectors helps in 3D models, animations, and special effects. In signals and processing, basis functions like wavelet basis are used to analyze and process signals. They help to decompose signal complex signals into simpler components, making analysis and compression more efficient. And the conclusion, the importance and relevance of basis and dimensions. Basis and dimensions are the fundamental concepts in linear algebra that play a critical role in various areas of mathematics, science, engineering, and beyond. Basis and dimension provides a powerful framework for understanding and analyzing vector spaces. They allows us to describe the size and shape of vector spaces, which is crucial in many mathematical and practical applications. By grasping these concepts, we unlock deeper insights into the structure and behavior of vectors and their spaces. Thank you.